In this lecture, we are going to talk more about transformations of the plane, but now we will discuss a new type of transformations called affine transformations. So that's a very interesting link between elementary geometry transformations. Between elementary geometry and linear algebra, which some of you have studied, some of you will study. So you can view this as a kind of a linking story. I'm not going to assume any linear algebra knowledge, though it will certainly help at some moment. So isometries, and especially things like reflections and parallel transports, translations, and so on, are probably relatively familiar notions for you because they appear a lot in geometry and in life in general. But affine transformations are maybe a little more unusual thing. So let me start with a definition. So a map F from R2 to R2 is called affine if, so first F is a bijection, and second, F sends any 3 points A, B, C on the same line to 3 points on the same line. So, okay, let's see. So, for instance, you take certain 3 points and they lie on the same line, and then the only condition is that they actually go to points on the same line, but this is supposed to be true for arbitrary triple of points. And a priori from this definition, it's absolutely not clear like what kind of transformations these are. Can we classify all of them or not? And we will actually classify all affine transformations and see how we can use them to solve problems. But this is quite a non-trivial problem. So a priori from this definition, it only preserves this what's called, so basically F preserves incidence relation, which means if you have a pair of a point and a line, then it basically preserves this. So it's not quite true that it follows immediately from here, because a priori I just know that 3 points go to, on the same line go to 3 points on the same line, but it's not obviously clear from here that all points on this line will go to points on this line, and maybe there are some other points which will go to this line as well. So before maybe giving examples, let me start with a very basic property. So maybe proposition. So F is affine, then for any 2 points A and B in R2 distinct, F is or maybe gives a bijection between line AB and F of A, F of B. So that looks completely obvious, but let me explain how to rigorously get it. So you take 2 points A and B on the same line, and then the statement is that if they go to certain pair of points A1, B1, then actually all points on this line will somehow go bijectively to points of its image. So in particular, if I call this line L, that's natural, I can call this line f of L. Okay, so let's prove it. so proof, and proof is as follows. Let's just take any other point. So clearly, so from the definition, points of the line AB are contained in the line A1, B1. So the fact that these points on this line AB go to points on the line A1, B1 is obvious, because for any such point, it lies on the same line as A and B, so its image should lie on the same line as A1, B1. But what we need to check, we need to take some point C1 on this line. So take C1 on the line A1, B1. And then we know, so let C be the pre-image of this point, and since F is a bijection, I know that this exists. So we need to show that the C lies on the line AB. So this is what we need to show, and assume it's wrong, so assume not. So then we have a certain point C here, and then we can look at lines BC and AC. And by the same reason we know that since points on the same line as A and C will go to points on the same line A1, C1, we know that all points of AC and BC go to the line A1, B1. And we are going to come with a contradiction with property 1. So take X, let X be any point in the plane, X any point in R2, and let's just draw a kind of a random line through it. So let's draw a random line. So draw a line, maybe let me call it A, B, C. So let's call this point maybe A prime, and this point B prime. So let's draw a line A prime, B prime, containing this point X, and this point A prime is on the line BC, and B prime is on the line AC. So I just and I assume that this is not equal to B and C, and this is not equal to A and C, and this is easy to see that one can do it. So I just draw kind of a random line through X, but then everything follows, because I know that F of A prime is contained inside my line A1, B1, because A prime is somewhere on the line AC, and F of B prime is contained on the line A1, B1. And so, in particular, any point on the line A prime, B prime will will go to the point of this line. So in particular, F of X is contained in line A1, B1. So F is not a bijection, because just the whole plane goes to one line. And so that's a contradiction, and that finishes the proof. So that's a little kind of elementary geometry argument, and of course I might have said immediately that F is a bijection sending lines to lines, but yeah, why don't we do a little geometry? So anyways, so now we know that lines go to lines, and for every line we just know that basically it's a bijection. When this line goes somewhere, and there is a bijection between its image and this line. And in particular, it follows that, so corollary is that F inverse is also affine. So for every affine transformation, we can take its inverse, which is affine. Obviously, identity is affine And also it's easy to deduce that composition is affine. So in this way we get a group. So affine transformations form a group, and let me introduce notation for it. Okay, I will do it on the next board. We conclude that affine transformations form a group. And the group is denoted by affine of R2. Okay, so examples. So what are some examples of affine transformations? So first is that isometries are affine. And in other words, I can say that the group of isometries is contained, it's a subgroup of the group of affine transformations. And that's more or less obvious because we know that if you take 3 points on the same line, yeah, they will go under an isometry to points in the same line. And we know that isometries are bijections. So that's pretty straightforward. And so now we have already a lot of affine transformations. So maybe we want something which is not an isometry, and that's also easy to do. So what we can do, we can take the following transformation. So this is something which is called homocity. So this is an example. So take a certain point O inside R2 and take a coefficient k, a real number not equal to 0. So the picture is, this is O, and there is this k. So let me assume for a second that it's not, that it is bigger than 0. So then what I do, for every point A, I take the line passing through O, and then I take, so for A in R2, consider A1 in R2 such that the vector OA1 is proportional to the vector OA with coefficient k. So if k is, for instance, 1/2, say, then maybe the picture is like this. That's A1. And if you think what happens if I take k equal to 1/2, it means basically just the point O is fixed, and then all points are becoming kind of twice closer to O, because like all the vectors are shortened twice. And this is a condition. And of course, for instance, if I do k equal to -1, then this h1/2, -1, that's called homocity. So this thing is called HOK, so like rotations. So then HO -1, every vector is going to the opposite vector. Point O is fixed, is just a symmetry with respect to the point O. So this is an isometry, but in general it's not an isometry. And what one can check, so a very easy fact, is that if you take any points A and B and compute the distance between f of A, here by f I mean this homocity. So if I take the image of point A and image of point B, the distance between them will change by the factor of absolute value of k. That's a little exercise. And another exercise is that this homocity HOK is affine. So let me maybe draw another picture. So if I think this is my O, and here I draw some elephant. So then when I do homocity, let's take k equal to 2, and then I will basically have to rescale everything by 2, and that's, you can imagine you kind of blow and you see a twice bigger elephant here. So this is an example of an affine transformations, and this is the goal of this exercise. So homosity is a good example. Is it true that every isometry is a composition of homosity and every affine transformation is a composition of isometry and homosity? No, it's not. So here is another example. Example number 3. So I can, after all, write down transformations in coordinates. Let me take coordinate line xy, coordinate system xy. And then I just want to define f by a formula. So f of a point xy will equal to x plus y comma y. So let's try to draw it. So if you look at every line parallel to the x line, this is a line with fixed y, so every such line will be fixed. So this line kind of slides along itself. And then if you take a point with y equal to 0, so here all points are fixed. So this is fixed. And for instance, if you take a line with a certain, and then if you take a line with a certain higher y, then it will shift. And the line with x equal to 0 will move to this line. And basically this point will go here, this point will go here, this point will go here. So you kind of boost everything here. If you take this square, for instance, this will go to a parallelogram like this. So everything is shifted. And for instance, if you take a elephant here, it will go to some kind of a moved and boosted, yeah, I don't know, changed, reshaped elephant. So that's the picture. You can practice a little bit. And this is also affine. And how to see that this is affine? Because let's take a line. So if you take a line L, and if you take a general line, it has equation ax plus by plus c equal to 0. So L consists of all points xy such that this equation holds. And then let's denote this is by x prime, this is by y prime. So we can try to figure out what happens with x prime, y prime. But then it's really easy to see that if x plus by plus c was equal to 0, then a times x prime plus b minus a y prime plus c equal to 0. Because if you plug in x plus y here and y, you will get ax plus by plus equal to 0. And so you will see that f of this line are basically points x prime, y prime, such that ax prime plus b minus a y prime plus c equal to 0. And so you see that a line goes to lines. So lines go to lines. Go to lines. So that's also an example of an affine transformation, and you can start to think that affine transformations are actually very complicated because it's, what is that actually? It's something quite weird. But it happens that algebra comes to save us here, and actually there is a very general formula for every affine transformation of this kind. Let's generalize the previous example. So 1, 2, 3, 4. So part 4 is a more general fact. So linear transformations are affine. So of course I need to explain what is a linear transformation here. And that's something which you in general learn in linear algebra, but I will specify here what's going on. So maybe let me so there are two ways to talk about linear transformations, with coordinates and without coordinates. So Let me do first with coordinates. So in coordinates, so let's take Cartesian coordinates. And this is some point O. And then we look at transformations f from R2 to R2, sending f of xy to ax plus by, comma cx plus dy, with ad minus bc not equal to 0. So this just gives a concrete formula for what is a linear transformation. And one can ask why, where this condition comes from. So this condition comes from because we want, so this guarantees, so this is equivalent to f being a bijection. One can easily check that. So if this is not true, if AD minus BC is equal to 0, it basically means that these two things are proportional always. And so the whole plane will be going to one line. So this is a bijection. And actually, this is where matrices come from, because if I can rewrite it as saying f of a vector xy, and now I'm going to write a vector as a column, equals to the matrix A, B, C, D times xy. And then, so I can denote it f of v equal a matrix A times v, where v is some vector. And actually, if you know multiplication of 2 by 2 matrices, this is where it comes from, because one can check. So linear transformations form a group and what happens if you compose them? So the corresponding matrices multiply. So matrices multiply. And so the statement is that if you take arbitrary linear transformation, then they form a group. So that's that they send lines to lines. One can easily check that basically arguing in coordinates, and the proof will be more or less like for the previous example. So let me leave it as an exercise. It's kind of boring. Linear transformations send lines to lines. Right. So, and we already have seen some examples. So notice that all of them fix the origin. So what were the examples of linear transformations we had? So in particular, we discussed this homosity, and in coordinates, if you choose O as a center, then everything is just rescaled by k. So it means x, y vector will go to a vector kx, ky, and so the corresponding matrix will be k, 0, 0, k. And another example was this xy goes to x plus y, and the corresponding matrix is 1, 1, 0, 1. And finally, one can take a rotation, and it's easy to see that it's also linear, and the corresponding matrix is actually cosine phi, sine phi, minus sine phi, cosine phi, and we kind of checked that when we discussed rotations. So these are some examples of linear transformations. Okay, So what else I want to say about that? So there is another definition of linear transformations which is more abstract, because this one just literally uses coordinates. And if you choose another coordinate system, for instance, you choose coordinates somewhat like this, you will get that the same geometrical transformation will be given by different metrics. So it's convenient to talk about it more abstractly. And so usually in linear algebra, basically what you say is that so f is linear if, well, firstly you will say that it fixes the origin. So in linear algebra you don't usually need that, because it will follow. And then the following holds. So first, for any two vectors, for any points x, y, or maybe, sorry, a, b we usually do here, a, b in R2, you say that f of a vector OA plus OB is a sum of vectors f of OA plus f of OB, and f of lambda OA equals lambda f of OA. And these two properties, so that's two, and these two properties basically guarantee you that if you choose this coordinate system, you will get something written in this form. One can check that, that's more or less immediate, because you just think, okay, let's take a vector 0, 1 and 1, 0, and you know that any vector xy will equal to, if I denote it by e1 and this by e2, equals x e1 plus y e2, and then it has to go, so f of xy has to be equal to x f of e1 plus y f of e2. And so if you denote this by a comma c and this by b comma d, and this can be arbitrary vectors, just not on the same line, then you will get exactly this formula. So basically, this abstract definition is gives you the same collection of maps as if you just write them down in coordinates in this way, though it's much more convenient to think in this form, because you don't need to choose this coordinate axis. And when you have a natural, geometric transformation, you usually describe it in a way, do this, do that, not just choose a coordinate system and then multiply something by something. So this is more what's called invariant form. So in linear algebra, you will define linear transformations like that, and then you will show that there is a bijection between linear transformations which are bijective and matrices which have this property which are invertible. So that's the idea. So all in all, we have a couple of examples of affine transformations. Isometries, including parallel transports, and then tons of examples fixing the origin. So homosity, and linear transformations of all sort. So basically there is these two types. And one can easily see that basically reflection and rotation and what else? Reflection and rotation are examples of linear maps. And for rotations, I already explained that, and one can easily check that for reflections with respect to a line passing through O. And so basically, so far we have just two types: linear maps and parallel transports. And these are distinct. So linear maps fix the origin, and parallel transport doesn't fix anything. So the main theorem I'm going to prove in the next lecture is a theorem saying that every affine transformation is a composition of a linear map and a parallel transport. So this is a fundamental classification theorem. It's not easy at all.